This is a story about three bubbles. Well, it's really about three bubble walls. Right? I imagine that I've got this pane of glass here, right? And I've got 3 points connected by 3 edges of bubble. So where do these bits of bubble end up intersecting? Right? This actually turns out to be an optimization problem. Bubbles want to be as small as possible. So less colorfully, this is what I'm really asking for. I imagine that I've got a triangle, and I'm trying to find a point in the middle of the triangle so that the sum of these 3 lengths, A plus B plus C, is as small as possible. I'm trying to minimize the total length of bubble. Let's make this concrete. Let's actually pick points and place the triangle at those points. And anyhow, we should be drawing a picture, right? We should be starting by drawing a picture. So for concreteness, I'm going to put the 3 vertices here at 0, 1, 0, 0, and 1, 0. And then what am I trying to do? Well, I'm trying to find a point, I'll call it XY, in the middle of this triangle so that these lengths, this length here, which I'm calling A, the length from XY to the origin that I'll call B, and the length from XY to the point 1, 0, which I'll call C, I want A plus B plus C to be as small as possible. I'm trying to minimize the sum of the lengths to the vertices. The way that I've set up this problem, the way that I've exactly positioned these 3 vertices, introduces a symmetry that we can exploit in this problem. This configuration is symmetric across the line y equals x, and the bubbles really shouldn't prefer one side or the other. I mean, what do bubbles know about left and right? So the solution, the point that minimizes the sum of the distances to these 3 vertices, should lie on this line. So I can say that its coordinates are x comma x. So what's the goal? So I'm trying to find the value of x so that this point x comma x minimizes the sum of the distances to the 3 vertices. Now, how do I write that down? Well, here's a formula for the sum of the distances to these 3 vertices. This first part, the square root of x squared plus x squared, that's just the Pythagorean theorem, right? How far is the point xx from the point 0, 0? Well, here's a right triangle, and the 2 legs of this right triangle both have length x, so the length of the hypotenuse is the square root of x squared plus x squared. What's, say, this term here? Where does the square root of 1 minus x squared plus x squared come from? Well, take a look at this little tiny right triangle here. This right triangle has this leg with length x and this leg with length 1 minus x. So how long is the hypotenuse, which is the distance from xx to 1, 0? Well, it's the square root of 1 minus x squared plus x squared. This last term, the square root of x squared plus 1 minus x squared, that's measuring the distance from 0, 1 down to xx. I can simplify this somewhat. This first term, the square root of x squared plus x squared, well, I could rewrite that as just the square root of 2x squared. And both of these terms are actually the same. It's just the addition is done in a different order, but of course it doesn't affect the value at all. So I can write this as 2 copies of just this first one, the square root of 1 minus x squared plus x squared. So that's a slightly easier way of writing f. We should also review if there's any constraints on this problem. I'm going to find it a little bit easier to deal with this problem if I assume that x is bigger than or equal to 0. In that case, the square root of 2x squared can be rewritten in an even easier way, right? The square root of x squared is the absolute value of x, but if I assume that x is bigger than or equal to 0, then I could rewrite this as just the square root of 2 times x plus, in this other term, 2 times the square root of 1 minus x squared plus x squared. So we've got our function of a single variable, so we can apply calculus. We can differentiate. So here we go. I want to differentiate this. F prime is, well, it's the derivative of a sum, which is the sum of the derivatives. So I first differentiate square root of 2 times x. That's just the square root of 2 plus, it's 2 times something, so it'll be 2 times the derivative of that thing, which is the derivative of 1 minus x squared plus x squared all into the square root. All right, and now I can keep on going here. I've got the square root of 2 plus 2 times, how do I differentiate a square root? Well, the derivative of the square root is 1 over 2 times the square root, but I use the chain rule. So it'll be 1 over 2 times the square root of the inside function here, which is 1 minus x squared plus x squared times the derivative of the inside function. So the derivative of 1 minus x squared plus x squared. I'll just do this again. So I got the square root of 2 plus, I can cancel this 2 and this 2. So I've got 1 over the square root of 1 minus x squared plus x squared times, I got to differentiate this sum, which is the sum of derivatives again. So the derivative of 1 minus x squared, that's 2 times 1 minus x times the derivative of the inside function. The derivative of 1 minus x is minus 1, plus the derivative of x squared, which is just 2x. So here's the derivative of f. With the derivative in hand, we can look for the critical points, places where the function either isn't differentiable or where the derivative is equal to 0. I don't have to worry about critical points where the derivative doesn't exist because this function is differentiable everywhere. So I'm just looking for values of x where the derivative is equal to 0. Let me rewrite this derivative even a little bit more nicely. So the derivative is the square root of 2 plus, and it's this thing I want to simplify a little bit here. What do I got? I got 2x, and then I've got another 2x here, so it's 4x minus 2. So 4x minus 2 over this denominator, the square root of 1 minus x squared plus x squared. All right, pretty good. And I'm looking for values of x where that thing's equal to 0. I'll subtract the square root of 2 from both sides. That means I'm looking for values of x so that 4x minus 2 over the square root of 1 minus x squared plus x squared is equal to negative the square root of 2. And then I'll multiply both sides by this denominator. And that means I'm looking for values of x so that 4x minus 2 is negative the square root of 2 times the square root of 1 minus x squared plus x squared. Now, how do I solve an equation like this? Well, one trick I can use is to square both sides. Now, that might introduce extra solutions, but I can go back then and figure out exactly which solution's still a solution to this original problem. So let's square both sides. So I've got 4x minus 2 squared is negative square root of 2 times 1 minus x squared plus x squared, this whole thing squared. And now I can expand that out a bit, right? What's 4x minus 2 squared? Well, that's 16x squared minus 16x plus 4. And what's this side? Well, squaring the negative gets rid of it. Squaring the square root of 2 is 2. And then the square of this thing, well, this is positive, so it's just whatever's inside the radical, which is 1 minus x squared plus x squared. Okay, so I got 16x squared minus 16x plus 4. I can expand this thing out, right? This is 1 minus 2x. And then here I've got a plus x squared and another x squared, so plus 2x squared. And I'll expand this whole side out, so it's 2 minus 4x plus 4x squared. And I'll subtract this from both sides, and I'll get 12x squared minus 12x plus 2 is equal to 0. So this is just a quadratic equation, right? And I can solve that quadratic equation by using, say, the quadratic formula. And I get that x is 1/2 1 plus or minus 1 over the square root of 3. Right? So this is an application of the quadratic equation to solve this quadratic. Now the issue here is that it turns out that I'm getting 2 solutions for x, but only one of these is actually a place where the derivative is equal to 0. So if you're careful and you check, it turns out that this is in fact a minus sign. So this is the only critical point. X equals 1/2 1 minus 1 over the square root of 3. So I've got a critical point. Let's draw a picture and see exactly where that critical point lands inside our triangle. So doing a bit of numerics, this critical point ends up being at 0.21. And yeah, I mean, I can plot that right here. This is the point x comma x when x is equal to this. And maybe that looks believable as where these bubble walls would intersect in order to minimize the sum of these three distances. There's more work to do. To actually show that that critical point does indeed give rise to the global minimum value of this function, we need to do more work. But let's put that off for now. Instead, I want to focus in on an angle calculation. In particular, I want to calculate this angle here, the angle that this bubble and this bubble make at the point where they intersect. And I can do that with a law of sines calculation, but I also need to know, say, the length of this piece of the bubble. And if you do a calculation, that turns out to be the square root of 2/3. All right, so I'm going to use the fact that I know this length. Ooh, and I also know this bottom length is 1. And I know this angle, right? The line y equals x makes a 45-degree angle with the x-axis. So I put all that information together into a law of sines calculation, right? Sine of pi over 4, that's this angle, a 45-degree angle, divided by the length of the opposite side, the square root of 2/3. Well, that's sine of theta divided by the length of the opposite side, which is 1. Now, I want to try to figure out what sine of theta is. Well, I've got all the bits of information here that I need. I know sine of pi over 4 is 1 over the square root of 2. So it's 1 over the square root of 2 divided by the square root of 2/3 is equal to sine of theta. And this, if you calculate it, is the square root of 3 over 2. Now, you might be tempted just to apply arcsine to the square root of 3 over 2, but you have to think a little bit about the domain here. Exactly where does this angle theta lie? It's not between 0 and 90 degrees. Theta, if you look at the picture, is bigger than 90 degrees. So I'm looking for an angle between, say, 90 and 180 degrees whose sine is the square root of 3 over 2. And that actually nails down theta for us. Theta is 2 pi over 3 radians, or 120 degrees. So these bubble walls meet at 120-degree angles. And we can see this for real in nature. Look at these 120-degree angles. The calculations that we're doing here are just symbols on the page, and yet somehow they manage to govern the real physical world, right? What do bubbles know about calculus? But somehow calculus knows about bubbles.